Okay, hi everyone. Welcome to our 10th Grammarly AI-NLP Club. I'm happy to see that so many people could join. My name is Mariana. I work here at Grammarly as a computational linguist, and I will be moderating tonight's meetup. This is our first event in the online format. The coronavirus pandemic hasn't subsided yet, as you know, but it shouldn't be the reason for us to cancel our events altogether, right? Instead, we decided to switch to all of our events to the online format. We'll keep this format at least by the end of this year, since our teams and guest safety is our highest priority. We hope that even in this format, we'll be able to help develop AI community in Ukraine and bring together beginners and experts in the fields of machine learning and natural language processing, and ultimately strengthen the reputation of Ukraine as a tech powerhouse and as an attractive place for research. The Grammarly AI-NLP Club is just one of the whole range of events we support and organize. I'm super excited to tell you that one of the largest international conferences in natural language processing, EACL, will take place in Kyiv next year in 2021. We expect up to 2,000 researchers. We keep our fingers crossed that we'll be able to do this conference, to organize this conference in the offline format. With the ability to join online, we expect up to 2,000 researchers and industry experts from the whole world. You may already know that we have the Grammarly AI platform. If you don't know about the Grammarly AI platform, that's the place where we upload videos and presentations of the awesome speakers whom we invite to our events. And in this way, we create a place for interesting and unique content for the Ukrainian AI community, which means for you guys, like these 52 attendees that joined today, for example. And if you haven't subscribed to Grammarly AI yet, go ahead, don't be shy. You just open your browser, type the grammarly.ai, and you can subscribe there and follow our events and also see all of the videos from the previous events and all of the presentations from the previous events that we hosted. In addition to inviting experts in the field of natural language processing at our AI-NLP clubs, we also provide an opportunity for you to connect with new interesting people, meaning like if you're one of those 52, like connecting with the other 51 people here. And today we will have our first online networking session. After the talk and the Q&A session, we are inviting you to different Zoom calls to chat in smaller groups. And in those smaller groups, you will be able to turn on your microphone and your camera and speak freely. There will be 4 different Zoom calls, and you can switch between them if you like. Depending on the room you join, you will have a chance to chat with our speaker, Elena, with Grammarly researchers, computational linguists, and Grammarly recruiters. You can find the links to these calls in your registration confirmation email, and Vika just also posted them, the information and about these Zoom calls into the Zoom chat, so you can find the link there too. Please join and enjoy good talks after our event, after our presentation. You'll be able to find like-minded people there and find out more about Grammarly, about talk to researchers and computational linguists in the field that work at Grammarly and also in other companies. And so that's it from me. Let's now get to the main part of today's meetup. I'm super excited to introduce you to our speaker, Elena Voita. And Lena just shared with us a tiny piece of information saying that she was born in Ukraine. So she already visited Ukraine and loves Kyiv, thinks Kyiv is a beautiful city. Lena is a PhD student from the University of Edinburgh and the University of Amsterdam. Previously, she spent 4 years at Yandex. I'm sure everybody knows what Yandex is. First, she worked at the core of Yandex web search, and then as a research scientist at Yandex Research, side by side with the Yandex Translate team. Lena strives to understand what exactly neural models learn and how they do that. And today she'll talk about models like BERT and ELMo, which I'm sure most of you heard of. If you have questions during Lena's talk, please type them in the chat. I will see those questions, and Lena will make pauses during her talk and take those questions so that you don't lose context and you're still on that topic. We will also have a general Q&A session at the end. Okay, all right. Lena, then I'm giving the word to you. And welcoming you.
Thank you. It's really, I was really happy to receive your invitation, and thank you for inviting me. And I'm really happy that Grammarly invited me because, yes, originally I'm Ukrainian and I have very warm feelings for Ukraine and for Kyiv especially. So, yeah. Today, I'm gonna talk about our recent paper with Ivan Titov, Information-Theoretic Problem with Minimum Description Length. Before we start, a little recap of what is going on in NLP. As you probably know, pretrained models have huge impact and are extremely popular. On the other side, analysis becomes vital in NLP. And of course, the combination of these two is a very important research area. Most of analysis in NLP tries to understand whether pre-trained models encode linguistic properties. And most of what we're going to talk about today is how to understand if a model captures a linguistic property. In the setting, usually you have a pre-trained model, for example, ELMo or BERT or whatever comes next, and you can get vector representations for your data. These representations may come from some layer of a network or a combination of them. It doesn't matter. What matters is that you have a pre-trained model and you use it to get vector representations for your data. And also you have labels for some linguistic tasks, for example, part of speech tags. Now, the question is, how can we understand that representations encode labels? What can be put here between representations and labels to be able to understand the relationships between them? Ideally, we would like to measure these relationships and to be able to say something like this layer or model encodes these labels better than that layer or model, right? For example, BERT is better than ELMo, or like first layer of BERT is better than second layer of BERT, or something like that. So what is going to happen? First, I'll show you the most popular approach of doing this, problem classifiers. Then I'll mention some sanity checks done in previous work. This sanity checks shows that standard probes have many problems. And this is our background. It's going to be very simple, but it's really important that you understand this part. So just in case, just to make sure we are all on the same page, here we'll stop for some questions. So this is going to be very short and very simple part, but if you have any questions, we'll stop here. Okay, then I'll present to you our approach, our new point of view on the task, if you want. And after this theoretical part, we will also stop for another set of questions. And finally, we'll come to the experiments and the final Q&A session. Okay, let's start. Standard approach, problem classifiers. Let's come again to the initial question. What can we put here between representations and labels to measure relationships between these? Standard problem puts here a classifier, so-called problem classifier. This classifier is trained to predict labels from representations. And as the measure of how well representations encode labels, usually use accuracy of this classifier. So let's spell it out one more time. The thing which is put between representations and labels is a classifier, which we call problem classifier or probe. Goal of this classifier is to predict labels, and measure we use is accuracy. I believe this type of problem is so popular that when people say probing for linguistic structure, they mean exactly this kind of probing. Well, it looks reasonable and simple, right? Yes, but you know, there's always some kind of but. But how about we do some sanity checks, just to make sure this method tells us something reasonable? Luckily, for sanity checks, we have some previous work we can look at. The sanity checks are different kinds of random baselines. For example, we can compare accuracies for representations which come from pre-trained model, for example, trained BERT, and a randomly initialized model. Surprisingly, accuracies are very close. So accuracy of a classifier, which is trained to predict labels for representations, says that a randomly initialized model is almost as good as a trained one. And this is this is not desirable because I don't know if you know how much time and resources it takes to train BERT. And if you after that, if you see that your model, which you trained like for enormous amount of time on several GPUs, is no better than randomly initialized one, it is not well, it's not what you would want, right? So to see differences in accuracies, because Well, we know there has to be some difference. The authors had to reduce the amount of probe training data. So for example, if we have only a small number of labels, classifier can learn something from representations which come from trained model, but it's really hard to do so for representations which come from random model. So it is easier to learn something from pre-trained model. Another type of random baselines is using random labels. This is so-called problem control tasks, which were introduced at ELMo last year. So here the idea is to measure how well we can, how well representations remember information about word type. So in the setting, each word type is assigned a random label, which is sampled from the empirical distribution of text. For example, here we have genuine linguistic labels. For example, we can see that cat is noun, but control task says that, okay, let's say that cat is a verb, right? And each token is assigned a random label, and a classifier is trained to predict these random labels. And again, surprisingly, the authors were not satisfied with how well accuracy of a classifier, which is trained to predict these labels, distinguishes between linguistic labels and random labels. So basically, a classifier, accuracy of a classifier says that a model encodes random labels almost as good as linguistic labels. And so the authors tried to tune a classifier setting, for example, tried different model size, and in the end, they reduced size of this probing model. And here we have a problem. We clearly see that accuracy of a classifier fails to properly distinguish different representations, for example, representations of trained model with random model, or linguistic labels and random labels. And what we want is a probing method which does not require a human to tell it what to say. And this is what we'll try to do today. So, okay, this is our background summary. What I need you to understand from this part, that the standard approach is to train a classifier to predict labels and to use accuracy as a measure. And previous work shows that this approach is not very good because it cannot distinguish between, for example, random models and trained models, or between how well a model encodes random labels or linguistic labels. So at this point, if something is not clear, let's deal with it before we come next.
I can see there's one person with a raised hand. I'm sorry, we cannot unmute you. If you have questions, please type those questions directly into the chat. Yeah, don't worry, we cannot bite you through the screen.
We won't even try.
Yeah, okay. Yeah, it looks like the introduction is fairly familiar to the rest of the community.
Okay,
I think we can continue.
So what do we do? Now let's come to, let's try to look at this task from a completely new perspective, from information-theoretic perspective. So once again, our initial question, what can be put here between representations and labels to be able to measure the relationships between them? And our idea can be summarized in just 2 sentences. Here they are. Regularity in representations with respect to labels can be exploited to compress the data. Better compression means stronger regularity, means representations better encode labels. So once again, regularity can be used to compress the data. Better compression means stronger regularity, means representations better encode labels. So now, if we, for the last time, if we ask our main question, what can we put here to measure the relationship between these two? Now we have an answer, a compression algorithm. If we have a compression algorithm, we can evaluate how good is compression, and therefore we can evaluate everything else. And at this point, I'm afraid most of you think something like, well, a compression algorithm looks like something really strange and complicated, and problem classifiers are very nice and easy, so we are never going to use it. Please don't. Please don't. Turns out that a problem classifier itself can be this compression algorithm. So now what I'm going to do is to make it clear, justify this theoretically, show how we can use simple classifiers and make them like serve as a compression algorithms, and we'll show you how it works in experiments. And for this, I will need some help from Alice and Bob. Be ready, Adventures of Alice, Bob, and the Data. Here are our heroes, Alice, Bob, and the mysterious so far data. Here we assume that Alice and Bob both know representations, right? So we have representations and labels. Here we assume that both Alice and Bob know representations, but only Alice knows labels. And this is our data. These labels, which only Alice knows, this is our data. Bob does not know them. So Bob asks, Alice, give me the data. But transmitting data is a lot of work. So what can Alice do? Alice can think for a start, and if she knows information theory, she can take a probabilistic model of data and to use it to compress the whole thing. So formally, the task is to compress data in an optimal way. It means that to compress data in a way that the number of bits we need to transmit this data is minimal. This optimal number of bits needed to transmit the data is minimum description length of labels known representations. And we'll call probes which measure this minimum description length or MDL as MDL probes. Now let's take a moment to realize what just happened. A probabilistic model of data can be used to compress this data. And we can set this model to be a problem classifier. This nice and easy problem classifier we all know how to deal with. And this is the main trick. This is the main trick. It turns out that we can convert a standard problem classifier into an MDL probe just by changing its goal. So if the goal of our classifier is to predict labels, then this is a standard probe, the one we discussed before, and the measure is accuracy. But if we change a goal from predicting labels to transmitting the data, to compressing the data, then the probe becomes MDL probe, and measure changes from accuracy to code length in bits needed to transmit this data. And the natural question is, why is this code length something better than accuracy? Well, if you paid attention, that here the thing which Alice sends to Bob is some combination of data and model. So why is that? Since Bob does not know the specific trained model that Alice used to compress the data, Bob needs to know this model somehow. So Alice has to send to Bob a model in one way or another. Otherwise, when he receives this compressed data, he wouldn't be able to decode the message. So in contrast, while standard probe tells you only about final quality, this is our accuracy classifier, right? It's final quality. Code length, in addition to final quality, it also tells how hard it is to achieve this quality, how hard it is to learn something from representations. And we'll call this two components, like data component, this is our compressed data, and the amount of effort component, like how hard it is to learn something. So we can learn something and have high accuracy. For example, we can learn a classifier to predict random labels, right? But we'll need a lot of effort to do so. And now I will explain how exactly this final quality and the amount of effort form the total code length, the description length of the model. And before we come further, one note. So here, by saying code length, we mean theoretical estimate of the optimal code length. So here, we are not going to transmit any data. We do not have Levin, Alice, and Bob. So we are not going to actually transmit the data, right? We just need a theoretical estimate of the optimal code length. For example, this data can be transmitted using like this number of bits, and we do not care how exactly we do the compression. Okay, so let's start with the final quality part. So this is only part of the code length. Here we assume that both Alice and Bob know the model P. So this is in this case, Bob already knows the model, and Alice doesn't need to say to transmit this model. Everything that Alice needs to do is just to compress data using this known model. In this case, the Shannon-Huffman code gives us the optimal bound on the code length. It states that there exists a code to compress labels with the code length as shown on the slide. And if the data are independent and come from the distribution pi, this bound is optimal. Now look at this code length. This is exactly cross-entropy loss evaluated on model pi, right? Therefore, in a way, learning is equivalent to compression. The task of compressing labels is equivalent to learning a model of data, because quality of the model, cross-entropy, is the code length needed to transmit the data. And this is the link between just problem classifier, right? This model pi, probabilistic model of data is a problem classifier, and information theory. So the task of learning labels, learning this model pi, training the classifier, is equivalent to compressing labels, because this quality of cross-entropy of trained model is code length needed to transmit the data. And now a couple of words of the term compression we're using. So usually compression is evaluated against uniform code. Uniform code does not require any learning from data. It assumes that all classes have the same probability, 1 over k, and for example, for one data point, we'll need logarithm 2 of k bits, and for the whole data set with n data points, we need n times logarithm 2k of bits. Okay? Okay, so, and now let's come to the amount of effort part, because this final quality, the cross-entropy of the model, is corresponds to accuracy of a classifier. So this part is the same. But for standard classifier, it's everything that the standard classifier tells, right? It's final quality or accuracy, which is the same. But for code length, it's only part of the total code length. So code length also tells the amount of effort component. Now, remember the main idea in 2 sentences. Regularity in representations can be used to compress the data. Better compression means stronger regularity, means representations better encode labels. So the amount of effort component is exactly about this strength of the regularity. How strong is the regularity in the data? And before I'll start, before I'm going to start scaring you with the formulas, let me give you an intuitive explanation. So on the slide, you see 2 sets of data points. So each dot corresponds to a data point, and colors correspond to linguistic labels. And actually, these are RT-SNP projections which come from the real data. So here are representations from the final layer of machine translation encoder, and these representations come from final layer of a language model. And labels correspond to CCG tags, which in a way which encodes syntactical information. So this is real data. And I assume you can clearly see that representations on the left here have strong regularity with respect to the labels. You can see it right away, right? And if representations have strong regularity with respect to labels, this regularity can be understood with less effort. And with less effort means that we either can use a very simple model to explain this regularity. For example, it will suffice to train a very small classifier, very small model to predict these labels very well, right? For example, like here, several linear planes. Or alternatively, if the regularity is strong, it can be revealed with a few examples. For example, here you see a much smaller data set, right? But it's still clear how to distinguish classes. And this is exactly how this vague so far notion of the amount of effort is translated into code length. So either, what we mean is the strong regularity can be either explained with a simple rule or with a small model, or it can be learned from a smaller data set. And these two ways of looking at the strength of the regularity correspond to two methods to evaluate code length. Because remember that a minimum description length is something theoretical, like it's the optimal bound, like how many bits we can use to transmit the data set. And these two are different methods to estimate this optimal code length in practice. And these methods are different in the way how they transmit the model. So variational code transmits model explicitly, and online code transmits model implicitly. And now we're going to look in more detail at each of them. But the intuition is right here. Basically, if you ever wonder how this works, just come back and imagine these pictures. When, how does it look when regularity is strong, and how does it look when regularity is not really that strong? Okay, variational code. Variational code transmits a model explicitly. It's so here I again ask some help from Alice and Bob. So what happens here? First, Alice trains a model of data. So basically she's training a problem classifier, the standard problem classifier, and uses it to compress the data. And to compress the data exactly the way we discussed before. So basically code length of the data is cross entropy of this trained classifier. So this is our data component, cross entropy. And then she first sends this model to Bob. First she sends model, and then she sends compressed data. So after that, Bob is able to decode the message. And this is the general pipeline of two-part codes. Two-part means that we have to send explicitly the thing which is needed to decode the message, in our case model, along with the message. So in our case, the message we want to transmit is labels the data, right? Here's the data. But to decode this message, Bob needs model, and we send this model explicitly. So again, I'm not going to scare you with formulas. For that, you can look at the paper. So now I'm going to explain you intuition behind. So the intuition is that we need to transmit the model along with the compressed data. And a variational code is an instance of this two-part code. And I know this looks scary, don't worry, nothing scary. So variational code is a particular instance of these two-part codes where it treats model weights, so the parameters of this problem classifier, as random variables. And in this case, with a little bit of math, you can show that the size of the model is scale divergence between prior distribution over parameters alpha and the learned one beta. And so for more details, take a look at the paper. Now a bit of intuition. So in two-part codes, we need somehow to transmit a model, right? It means we have to transmit all parameters of the model. But deep learning models are very, very big, right? And if we were to transmit them in a straightforward way, it would be highly inefficient, and it wouldn't make much sense. But variational code, it treats each model parameter as a random variable. And this is a very neat trick, because when you train a variational model, when each your parameter is a distribution, once a model is trained, you can see that some weights will have high variance. And the weights, the parameters of the model which have high variance can be transmitted with lower precision. So if a weight has high variance, it means that we don't care much about its value, right? It can be either of some range, right? It means that for some weights, you'll need only a few bits to transmit them. And this is how variational code is able to transmit model parameters efficiently, because some of the parameters are important and will require high precision and a lot of bits, but other parameters are not important and will require only a few bits. And for theoretical justification, you can either look at the paper or at the bits-back argument. It's the classical result from information theory, which connects this variational learning and two-part codes. What is also interesting when we use variational models, we can choose priors in a peculiar way. So the specific model we use for variational learning, which is called Bayesian compression, it uses priors over parameters in a way that once a model is trained, we can prune some neurons from a model, like shown on this picture. So again, for the details, you can look at the paper, but the idea is that by choosing some priors over parameters, we can make sure that some of the neurons are pruned. It means that for variational learning, we will be able to look at model size in two ways. So the code length, this K term, this theoretical K term, but we will also be able to look at the pruned probe architecture. So if we train a classifier and we'll get this like small pruned model, we can see that, okay, maybe if the model is small, then the regularity is strong. And once again, what do we expect to see using variational code? So if regularity in representations is strong, it can be explained with a simple rule. With a simple rule means using a small probing model, a small classifier. A small classifier means easy to communicate, so only a few parameters require high precision. And as we will see, often classifiers with the same accuracy may come with very different model cost, with different amount of effort. And this is important that variational code gives model size as a byproduct of training. So we don't have to do any manual search. So we just train a model and we'll get model size as a byproduct of training. And this is different from previous work, which tried to tune manually for the size. Okay, to sum up, variational code transmits model explicitly. We will get model size as a byproduct of training. And as we will see in the experiments, often probing classifiers which have very similar accuracy can come with a very different model cost. Okay, and now we'll come to the next, to another way of looking at the amount of effort component, online code. Online code is a way to transmit a model implicitly. It means that nowhere, so differently from variational code, where we just took model parameters and sent them to Bob, here we won't do that. So how does it work? In this setting, Alice and Bob agree on the form of the model, hyperparameters, random seeds, and basically the whole training pipeline. Also, they choose time steps at which they split data set. And Alice sends data by portions. So first, this is how we split our data set in increasing portions of data. And first, Alice sends this first small portion without compression. And without compression, it means uniform code. And for this, she doesn't need to send the model, right? Because there is no model. Then, after that, both Alice and Bob have the first portion of data. And they both use it to train a classifier on the small part of data. And since they agreed on the whole training pipeline, they can do this and to get exactly the same model. And Alice uses this model to compress the next portion. right? And she sends this next compressed portion to Bob. And she can do this without sending a model, because Bob has the same model that Alice is using to compress the data, right? So at the next step, again, now Alice and Bob both have first two portions of the data, and they use all this data to train a new classifier. And again, Alice can use this classifier, this model, to compress the next portion and send it to Bob, because again, at this point, Bob knows which model Alice is using. And this continues until the whole data set has been transmitted. So here at each step, the model trained on all previous data is used to compress the next portion. And this happens iteratively until the whole data set is transmitted. And the code length in this case is the first portion compressed with no compression, right? Is transmitted with the uniform code. Remember, right, with uniform code, this is logarithm k, it's a number of bits for one data point, and T1 is the size of the first portion. So this is the first portion with no compression. And the next, it's code length for each of the next portions compressed with the model trained on the previously transmitted data. And this is cross-entropy loss of the model. It's the data component we discussed before, right? And here, since we are not transmitting the model, we don't have this model component, but we would like to have something we could interpret as model component, because this will be our amount of effort. Because this is, in the end, this is what we want, because final quality we could get using accuracy of a classifier, right? But code length, we need to get something more. And we can get something like amount of effort for online code by subtracting the data code length. So the data code length is cross entropy of the model trained on all data, and this is code length if we know a model, right? If Bob knows the model, this is our code length. And online code length is code length if we don't know a model. So if we subtract these two, this can be interpreted as the amount of effort component. And this is similar to variational code. So in variational code, it has the data component and it has model component, which evaluated a bit differently. And a bit of intuition again. So what we expect to see with online code. If representations have strong regularity with respect to labels, this regularity can be understood with less effort, which in this case means it can be learned with a few examples. And remember, since we're and learned with a few examples, it means that somewhere early in the transmission process, our models are already very good, and they are very good at compressing the data, almost as the model trained on all data set would do. And this also related to area on the learning curve, which plots quality as a function of the data set length, right? So for each, so for small data set, we have one quality. For a bit bigger data set, we have another quality. And so basically, online code tells you how easy it is to learn from smaller data sets. Okay, online code is a way to transmit data without transmission model explicitly, and intuitively it says how easy it is to learn from smaller data sets. And now it's one point, how it relates to previous work. It's a really interesting observation. So if you remember, to see differences in accuracies with different kinds of random baselines, with either a random model or random labels, previous work had to either reduce a probe model size to use very small classifiers, or to reduce the amount of probe training data. For example, we have a lot of data with part of speech tags, but we use only a small part of it to just to see the difference between trained model and randomly initialized one. So if you think about it, that the first one is a way to indirectly, manually force a classifier to account for the amount of effort component in variational code, right? By reducing the model size. We force the model, like to force a classifier to say how hard it is to learn with a small model. And the second is the way to indirectly, manually force a classifier to account for this amount of effort component of online code. Because if we force a classifier to use only a small data set, it's like forcing it to tell how hard it is to learn from small data sets. And this will more like observations. So if we reduce a model size, we'll see larger differences in accuracies. If we reduce the amount of training data, we will see larger differences. But description length has this amount of effort component directly by design in theoretically justified way. And depending on the specific method used to evaluate this description length, this amount of effort component can tell either how hard it is to learn with smaller models as in variational code, or how hard it is to learn using smaller data set as an online code. Okay, at this point, if you have any questions, I'll be happy to answer.
Yeah, we have a couple of questions here in the chat. The first question is, when we evaluate the compressed data size, do we take into account the size of the model that we need to transmit, or do we only care about the data that we compress?
In the data component, we only care about data. So yes, so data, here, the data component, it's only, here we assume that we already know a model. And if we know, provided we already know a model, we can use this model to transmit the data with such and such code length using this cross entropy. And this is the same data code length, which is later used in the variational code. And here, if you remember, so here Alice, she first sends a model. And when Bob knows a model, she sends the data. And this data component, it is assumed that Bob already knows a model. And in online code, again, when we talk about data code length, at each step when Alice sends the new compressed data, here the difference is that Bob also knows a model, but he knows that not because Alice sent a model, right? But because he trained the same model using his data. Right? So everywhere here, when Bob receives compressed data, he already, one way or another, he knows the model that Alice used.
Mm-hmm. I see. And another question has to do with the Bayesian compression that you mentioned. So in the Bayesian compression setting, how do you choose prior for weights?
It's not me who choose priors, it's Christos Leizes from University of Amsterdam. Yeah, but actually it's a long story. And I'm not sure I'm an expert to say this. So basically, if your prior distribution is chosen in a way that so let's say, well, it's really hard to explain in a couple of words. But for example, in simple setting, your prior, say, is a normal distribution, right? And when it's normal distribution, you kind of, so you have mean and you have variance. And if you still can get like a small variance, which means that your weights are like almost constant, right? And or you have a high variance, which means something else. But nowhere, well, within a normal price, you won't get discrete solutions either, like the weight is constant or not, right? All this, and probably you won't get a very high variance. And so here the trick is that some weights will have very high variance. And if they have high variance, that means that we can prune them, right? We can set any value we want, for example, 0. And this is the whole line of work trying to do this. It's not the only method which does this. There was a line of work started with the variational dropout, which chose this priors for specific model parameters. And this method we are using from Amsterdam group, where they tried to to induce a group sparsity, to make priors, so how it is different from variational dropout, where priors are for each weight. So here it means that for all weights which belong to the same neuron, we have the same parameter for variance. So if we prune, if something has high variance, it reduces like the whole neuron, because it's connected to all the weights which come to this neuron. But the way to choose priors, it's a very long story. I suggest you look at the original paper. Like
well, let's say that Bayesian compression is a very long story and deserves a separate talk about it.
Variational methods as a whole, so it's a very, very long story, yeah.
Mm-hmm. Yeah, and we have another question that is it's easier if you open the chat if you can to see, because this is kind of a visual question more. So we need to manually work. We need manual work to filter the noise from decompression. Do we need manual work to filter the noise from decompression? Like basically, how much information is lost? I guess that's what the question is.
I cannot open the chat, but
okay. That's okay. So the general question is, do we need to filter the noise from decompression? Mm-hmm.
Since we are not going to transmit the data exactly, right? So we're not considering the specific algorithms we use for transmitting. So our variational code and online code, it's a way to estimate this theoretical bound, right? For example, when we say the data code length is cross entropy of the model, we mean that this is an optimal theoretical estimate. We are not saying here, for example, that we are using the Huffman code to encode in this and that way, right? And we'll spend this and that number of bits, and this is happens losslessly. And so we do not care about that. What we do care about is how well our methods estimate this theoretical code lengths. And this is something we'll discuss in the experiment section.
Mm-hmm.
So everywhere, so basically we used here estimates for data code lengths, right? And for data code lengths, their bound is optimal. It means that for online code, for example, everywhere we send data, and which is basically everywhere, the bound is optimal. And since, as we show in the experiments, it agrees, the total code length agrees very well with variational code, we can say that the model component in variational code is also in some sense optimal.
Mm-hmm.
So the short answer is no, we do not need to care about boundaries. Yeah.
Okay. Yeah, I think we're ready for the experiment session then.
Okay, yay, experiments. So in the experiments, as you remember, we had at the very beginning, when I told you about sanity checks, we had two types of random baselines. When we used random labels and it compared to linguistic labels, and when we used random initialized model and compared to pretrained model. So here I'm going to talk about only the first part, because we will need to finish at some point, right? And the second one, if you're interested, take a look at the paper or at the blog post. So, okay, description lengths and random labels or control tasks. So first, let me remind you what is the control task. Control task is something which is defined for like to pair a certain linguistic task. For example, here it's shown for part of speech tags. In this setting, each word type, and word type means token cat, whatever it appears, like not cat in this sentence, but cat in all sentences we see. Right? Each word type is assigned a random label. Labels are sampled from the empirical distribution of tags. For example, it means that we know that, I don't know, 10% of all words we will have usually have noun tags. So in this, among these random labels, the distribution between this fake part of speech is approximately the same. And these labels are fixed and do not depend on context. So if we say that cat is assigned a label of verb, it will have this label with no regard of context where it appears. So everywhere a cat appears, it will be assigned the same tag. And intuitively, these tasks measure the ability to remember from word type, because these labels only depend on word type and do not depend on context, which is different from the linguistic labels, where the same word type can have different, can be basically different part of speech depending on context. Okay, so what we are going to look at. First, we're going to make sure that the two compression methods agree in the results, and this relates to the question. It was actually a very good question. So we want to evaluate this theoretical thing. So minimum description length is the theoretical thing, and variational and untimed code are different ways to estimate this optimal theoretical code length in practice, right? And first, we'll make sure that these two practical ways to evaluate this theoretical thing agree in the results. And this will be a good sign. And it will be a good sign. Next, we'll see that description length identifies control tasks or these random labels easily, while accuracy does not. Then we'll look at this model component on the amount of effort, which is what we wanted, and we'll see that for linguistic task it takes less effort to learn because the strength of regularity, right? And for control task, it will require like a lot of effort to learn something. And finally, we'll look at stability among hyperparameters and random sets. Okay, so here are our results. In these experiments, we used ELMo model. ELMo has, so here's the embedding layer and 2 layers of ELMo. Here we show accuracy, and the results are shown in pairs. So first linguistic task, then control task. So this is true labels, and the second number is for random labels, right? And this is description length for both codes we looked at. So first we see that for linguistic task left part, right? For linguistic task, the best layer is the first because minimum the code length is smaller, right? And also we see a large difference between layer 0 and contextual representations. Because in accuracy, well, it's not really clear what's going on. But code lengths, we can see that, for example, this embedding layer code length is like twice bigger than for the first layer, and that means that basically the first layer has context and the regularity is stronger in the first layer. Next, we see that for random labels, scores become larger as we move up, which is expected because these control tasks measure the ability to remember from word type, because these random labels depend on word type. So on the embedding layer, it's easier to predict. As we move up from the embedding layer, it becomes harder and harder. Okay, and also we see that for both our compression methods, we see that code lengths for random labels are a lot bigger than for linguistic task. And this is what we wanted. So basically it says that the amount of effort, we will look in more detail a bit later, but the amount of effort for random labels is very high. It's very high. So this difference between linguistic task and control, if we look at code length, it's very huge. Sorry, it's really huge. And looking at accuracy, we cannot even say that. And what is especially interesting is the embedding layer. So here, actually, the results contradict each other, the results of standard probes and MDL probing. So if we look at accuracy, we'll see that for control task, accuracy is higher. So basically, accuracy says that the model encodes random labels better than linguistic labels. And this is crazy because model cannot possibly encode random labels better than real linguistic ones, right? But accuracy says exactly this. And this is kind of expected because for control tasks, labels are fixed for word type, but for part of speech tags, you need context for some words, which can have different part of speech depending on context. We cannot predict it from the first layer. But code length shows that actually random labels are a lot harder to predict because code length for random labels is almost twice larger than for linguistic task, right? Almost twice large. And why that's happening? So let's look at their model and data component of the total code length. This is variational code, online code, and for each task we show the total code length split into data and model component. And first we see that for control task, this amount of effort component, orange one, is very big, right? So we can clearly see that it is really hard to learn random labels. So we can do that. Our model can do that, but it is really hard. It requires a lot of effort. And this is very different from the linguistic task. Here you see that most of the code length is a data component. So you need to spend a lot of bits to transmit data, but your model is very small, right? In both code, in both methods. And especially interesting if we look at this layer 0, where accuracy is higher for control task, and this is why the data component is smaller for control task. See, so the data component is smaller. It means that the data compressed better for control task, and this corresponds to accuracy. That's why accuracy was better for control task. But the amount of effort is very high, and this is why is one of the main illustrations how this description length is better than accuracy, because accuracy tells you only about this data component. It is only part of the story. So when you look at the representations, you need to understand first whether information is contained in these representations at all, whether the information is there, right? And then you need to look at how strong is the regularity, so how hard it is to extract this information. A small example, for example, Buddhist people say that we are all able to remember our past lives, right? Maybe we have this knowledge, but how hard it is to extract this information, right? This is basically what happens. So representations have information about these random labels, but it is really hard to extract it. On the contrary, for real linguistic labels, it's really easy to extract because representations have structure with respect to this linguistic labels. Yeah, so basically what I was saying, so the code length is smaller, which means that accuracy is higher, which is what we saw, but the amount of effort for control task is very big. Okay. A couple of words about online code. Remember that online code relates to area and the learning curve. So here we are showing learning curves, which plot quality as a function of the amount of data. And you can see that, so solid lines for linguistic task, dashed lines for control task. So here you can see that linguistic task labels can be learned very well using even small data sets, like 0.1% of the whole training data set. And for linguistic task, we already have quite good quality, right? And the quality is very good even when we are using smaller data sets. But for control task, for random labels, it is really hard to learn from smaller data sets. See, and so the amount of effort is basically, in a way, the difference between the solid and dashed line. So this is amount of effort, like how hard it is to learn from smaller data sets. Okay, and as I promised, we can now look at their induced probe architecture. So for variational code, by using this Bayesian compression, we can get a sparse probe architecture. So everywhere, for all experiments, we start with the large probe. Like it's thousand neurons in each layer. It's a two-layered multi-layer perceptron. And this is the final compressed models. And what we see is that for linguistic task, the pruned architectures are very small, right? So like 30, 70 neurons at top layers. And this is for 45 labels. So this is like pretty small models, right? But for control task, models are larger. And this is again characterizes as how strong is the regularity in the data. So to learn linguistic labels, it's enough to have small problem classifiers, right? But to learn random labels, we need a larger model capacity, okay? And again, variational code gives this as a byproduct of training. So we didn't need to tune probe hyperparameters. We didn't need to like search through different architectures. We just got it as a byproduct of training. Okay, and the final part is stability. So when you're using standard problem classifier, it is not clear which hyperparameters to choose. For example, you can have 2 layers classifier, you can have 1 layer classifier, you can have different number of neurons in this classifier, like 1,000, 500, 250, 150, right? It's just for the example. And you don't know how to choose it, and you don't know any criteria to choose the hyperparameters. And what is really bad is that results of standard probe depend on the choice of hyperparameters. For example, for these hyperparameters, we see that control task is better. Again, this is what we saw, right? For layer 0, accuracy is higher for almost all settings. And for some of the settings, the results tell that linguistic task is encoded better. And this is not good because depending on how we choose this probe hyperparameters, we can get different results. And this is the whole like point of probing, to know to let it show what really is what's really going on. Well, it cannot possibly answer this question, right? While for MDL probe for code lengths, we see that for all settings, the results are the same. So you don't need to worry about probe hyperparameters in the MDL probing, because MDL probing is stable and it characterizes not only final quality, which can be different, right? But also the amount of effort, and the results do not change depending on these hyperparameters. And what is more fun, results of standard probing can change even when you tune random seeds. For example, here are the results for 5 random seeds. So hyperparameters are the same. We change on the random seed. And here we get different results depending even on random seed. So how are you supposed to understand which layer better encodes something when you getting different results depending on your random seed? And even if you want to like run the algorithm 5 times and see that, okay, probably this is better because it's like the most common results, but still scores are very close and it's hard to make any conclusions as to which layer is better. But for code lengths, the results are the same, they're stable, and the layers are well separated. So here we don't need to be worried about which layer is the best. Of course, in all experiments, we can clearly see that for the first layer, code length is smaller, it means better compression, it means stronger regularity, and so on and so forth. Okay, and for other type of random baselines, you can look at in the paper. Okay, finally, conclusions. We propose information-theoretic probing, which measures description length of labels given representations. We show that it naturally characterizes not only probe quality, but also the amount of effort needed to achieve it. And as we saw in the experiments, this is a really important thing to look at. We explain how to easily measure MDL on top of standard probe training pipelines, and we show that results of MDL probing are more informative, stable, and sensible than the results of standard probes. But if you really if you want to remember 1 or 2 sentences from today's talk, here they are. So this is basically the only thing I need you to understand. Regularity can be used to compress the data. Better compression, stronger regularity, representation, better encode labels. So that's it. For more details, you can look at the blog post, and also you can find there's a blog post for my other work, also for machine translation, for context-aware machine translation, and that's it. Thank you.
Elena, we have a couple of questions. Yeah, folks, please post your questions into the chat. So the first question that I have is related to some of the experience that they had with learning how neural networks learn, you know, exactly what you were talking about. So last year I attended a summer school, this ASLI summer school. This is a summer school in language logic and computation. And we had a very nice class on learning how neural networks learn quantifiers. And so we were comparing how neural networks learn quantifiers, and there are simpler quantifiers and more complex quantifiers, versus how humans do that. And the teacher did an experiment in class where the teacher showed us like a couple of circles that were randomly painted in different colors. And then we were supposed to learn the quantifier after he showed us a couple of pictures of those, you know, colored circles. So I was wondering whether there's any comparison versus how well humans learn the proper parts of speech for words versus learning randomly assigned tags for words.
Oh god, there's a lot of work trying to compare how of the kind like how neural networks do things, how humans do things, but luckily for humans, I haven't seen humans who were asked to learn random labels for part of speech. No, so for this kind of tasks, no, but you know, there are different kinds of like connections between cognitive psychology and natural language processing. And for example, recently I've seen the paper where they used language model to predict reading speed of humans, so such kind of things. But usually they're very far away from let's say that the set of experiments you can do on humans is very limited. So for these experiments, no, but yeah. So this work for the kind of things which are useful for practical reasons. And when it comes to humans, there are usually much smaller data sets, very synthetic tasks, something.
Yeah, I just feel that for a task like this, if you're taking part of speech tagging, then you can just take a university class or something and experiment with students there. So it should be harmless for them.
Learn the random labels, it's too harsh.
Yeah. We actually took a small vote in the chat, and we have 100% votes for learning proper parts of speech, that it's easier to do for humans than to learn randomly assigned tags. Because I guess learning randomly assigned text for words is like word-for-word translation. You basically learn the whole vocabulary. And stuff. Another question that we have, shouldn't learning curves work just as well for classic probes as they do for the online codes? Like train the probing classifier on different amount of data and compare area under curve for control and linguistic tasks.
This is exactly it. Yes, this is exactly it. It's just, yeah, and actually there were a couple of attempts to use this learning curves, like in addition to accuracies and transfer learning settings, and this is a reasonable thing to do. Yes, and it turns out that it has theoretical connection to code lengths, and it's actually like it's always better when you understand like on more high level like what you're doing. So here you're basically indirectly by plotting learning curve, you're indirectly estimating this description length, and you have this amount of effort like showing how hard it is to learn from different amount of data. But you either may know about it, or you may not know about it, but basically it is the same. Yes.
Awesome. And is there a Colab notebook that you can play with available from you for this task, for example?
No, but
or a GitHub repository,
yes,
something like that.
GitHub repository. There's GitHub repository.
Yeah. Do you have a link anywhere in the presentation, or we can just send it later with the send out for?
You can find in the paper, in the blog post.
Okay. Great. Okay, so the button view code is leads you to
the button
GitHub.
view code, and if you open the paper, it's like on the first page, like the code is here. Yeah.
Okay. Great. Okay, another question arrived. How much is MDL harder to use in practice? Like implementation-wise, isn't it more complicated? And what about training time versus plain probes?
It's a really good question. I wish I didn't have to answer it, but yeah, so the reality is the following. So with online code is a very simple implementation-wise, because you have your probe training pipeline and you just have to like launch several times with different amount of data. You just split your data set, you train on the first portion, the first two, and so on and so forth. So in terms of implementation, it's like you don't have to do anything, but yes, you do have to train your classifier several times for different amount of data. So it's gonna be a little bit longer. But luckily for us, probe and tasks are not so huge. Probe and classifiers are not so huge. So like, if you need 1 hour to train a standard probe, it takes like 3 or 4 hours to evaluate on one code length, for example. With variational code, it's not so straightforward, maybe because I'm not a big fan of variational learning, but for variational code, you would have to replace all layers in your probe and classifier with variational layers. You can do it quite easily if you're comfortable with variational learning. Basically, you just need to like take this repository from Bison compression. They have feed-forward layers, and so you have problem classifier with 2 feed-forward layers. You replace these layers with variational layers with defined operations like forward, backward, and that's it. But you need to when training, you need to change loss function because variational learning, so standard learning is like only cross entropy, right? You optimize on this classification loss, but in variational learning, you will also have part of the loss which correspond to the scale divergence, because this is a variational model, you have to train it somehow. And you also have to make sure the coefficients between these two losses are correct in the sense that as you go over the whole epoch on your data set, coefficient between in front of this model component has to be exactly 1. So if you're training with batches, so you have your data set, you have a lot of batches, you need to make sure the coefficient between loss in front of scale divergence, which is model component, is such that when you add up over all batches, you will have exactly 1. So these are like minor inconveniences. So practically speaking, to sum up, online code is easy. You don't need to change anything. You just need to launch it several times. But with variational learning, you have to do some coding. So you need to replace layers and you need to add loss term.
Well, I hope you mean minor inconveniences, but by minor inconveniences, because usually when someone says minor inconveniences, it means that you will spend a couple hours debugging your code, and until it works.
Yes, you will. Yes, you will. But the whole point of our paper is that I did it for you. I showed that these two methods agree in the results, so you could use online code. So basically, you can use online code and be sure that it agrees with variational and it's good at estimating this theoretical thing we care about. So I did it, I suffered, but you don't have to.
That makes sense. Thank you. Using online code, I think, will be easier for everyone else to do.
Now already several papers are using it, and like no one complained so far.
That's great. So we don't have any additional questions in the chat, but I'm sure that we will have more questions in our networking session. Yeah, so guys, if you want, you can send your claps or smiley faces or anything you want to send. Thank yous to Elena.